This is a lab on projectile motion. To begin with, the goal of this lab was to compare the trajectory of a circular object in projectile motion to two simulations of the object in projectile motion. The first simulation essentially only recorded the effect from gravity on the object, and the second simulation recorded the effect from gravity and the drag force. The purpose of this lab was to demonstrate the concepts of drag force and gravitational force in projectile motion. In this lab, I utilized Newton's second law, or the momentum principle, and the drag force formula. In addition, I used GlowScript for coding for the simulations and Tracker to observe my experiment video. In short, when only gravity is acting on an object in projectile motion, it will travel a farther distance. However, when drag force and gravity are included, the object will travel a lesser distance. As previously mentioned, I used the drag force formula and Newton's second law. The drag force formula is equal to negative b times velocity squared times the velocity unit vector. In order to find b, I found where the terminal velocity occurred where there's no net force on the object. At terminal velocity, the force from gravity was set equal to the force from the drag force, which helped me find b to be equal to mass times the gravity divided by velocity squared. And then the Newton's second law is where the net force is equal to the change in momentum over change in time, which basically means that with the zero net force, velocity will be constant. However, when a force is applied, velocity will not be constant. In the experiment, I utilized a ruler for calibration for the system. I used a flat table and a wadded up paper ball. In the experiment, I took the ball and threw it in both a forward and upward motion across the table and recorded its trajectory. Next, in the simulations, first for the gravitational only simulation, here's the coding. First, I defined the sphere, arrows, graph, and the initial position of velocity vectors based on my original experiment video. Next, I defined the mass and used delta t to update time in each while loop. Next, in the while loop, I first defined net force to be including the gravitational force, and then updated ball velocity and position using Newton's second law. I repeated this loop until time was equal to 0.333 seconds, or whenever the original experiment video ended. And finally, I plotted the position and velocity curve. Next, in the second simulation, including gravitational force and the drag force on the object, I did the same step of code. However, whenever setting the net force, I included both the gravitational force and the drag force. Here's the model for the gravitational force and the model for the drag and gravitational force. And now here's the graphs of the two simulations and the experiment data. The green is the drag force and the gravitational force. The blue is only including gravitational force, and the orange is experimental. As you can see, all of the graphs follow the similar trajectory. However, the experiment traveled the furthest, and the drag force traveled the least distance, the smallest distance. However, the drag force was expected to travel the least distance. However, the experiment traveling a little bit further than the actual simulation that only included gravity could be due to some of these errors, such as the paper ball I created was not a perfect sphere as used in the simulation, which means that basically the trajectory of the ball was harder to predict than a perfect sphere that had an even amount of drag force being applied. In addition, there could have been some errors in Tracker when Tracker took the data from the video. As in the experiment video, I threw the ball forward and Tracker recorded that initial velocity. However, there could have been some errors there which could have caused the initial velocity to actually been faster, which means that, of course, the ball would be going a further distance because I threw it at a faster rate than recorded in the simulations. And finally, some questions. Terminal velocity basically occurs where net force is equal to 0. And in the drag force and gravity model, it didn't reach enough time to fully reach terminal velocity, where basically the drag force would be equal to the gravity force. So if I was creating a new experiment, I would increase the initial position height so there'd be more time for these forces to equal out and for true terminal velocity to actually be recorded. And the second question being, what would happen if the object were initially thrown just straight up? Most likely the object would take longer to reach the ground. With no x component in velocity, the y component of velocity would be equal to the net velocity, which means that the y velocity would be greater and the object would reach a higher position in the y component, which means that there would be a further distance for it to reach the ground. Thank you.